Good afternoon. I'm Dr. Peter Irvin, a lecturer at UCL, Earth Sciences Department, and it's my pleasure to introduce Dr. Eloise Marais. Dr. Marais leads the UCL Atmospheric Composition Air Quality Research Group, which uses numerical models to understand the effects of humans on the chemical composition of the atmosphere and the impacts of these changes on air quality, climate, and public health. Dr. Marais obtained her PhD from Harvard University and has worked at the University of Birmingham and Leicester since then, before starting her current position as an associate professor at UCL. Dr. Marais' recent work has contributed to the emerging public debate on the potential influence of a growing space industry on the environment, which is what she'll be talking about today. In this, after she's given her presentation, we'll be using the Slido service to ask questions and hand them over to Dr. Marais. That's sli.do, and you'll use the code UCL space, all one word, to access that. And yeah, let me hand over to Dr. Eloise Marais, who'll be talking about the billionaire space tourism race and how it could be one giant leap for air pollution.
Thank you very much, Pete, for the kind introduction. And to the organizers of the UCL Lunch Hour lecture series for including me on what is a very dynamic and interesting program. So hopefully I can do justice to it by taking you through the space tourism race that's taking place currently, and also share some of the results that we're obtaining within our research group to try and understand what a formidable space tourism industry might do to the environment, and hopefully invoke some policy action as a result. I should also acknowledge that much of the research results that I'm going to show are being carried out by Rob Ryan, who's a research fellow in my research group. There was also a component that was conducted by Chloe Bell-Hatchett, who is now at University of Cambridge, who conducted research over the summer within our research group, and of course a collaborator, Seb Eastham, who is based at MIT. We've seen that the modern space sector has evolved substantially since the first space race, where it was mostly dominated by Russia and the US. And you can see this kind of evolve through this time series that's shown on the slide. We're seeing now that there's many more countries that are becoming involved. India and China now have a formidable space industry. The European Union, of course, contributes substantially to the space industry. And we now have quite a large private sector with their technological advancements that have led to space launches being considerably cheaper, which has also contributed to substantial recent growth in the space industry. We can also see that in this time series from 2005 onwards, we're starting to see a substantial ramp up in the number of launches that are being carried out after quite a lull in rocket launches. Where we've seen in the recent past about a 6% per year growth in the number of launches. And this doesn't go all the way to 2019, a year that we focused on to put together an initial estimate of air pollutant emissions from rocket launches, where I'm just indicating where we're at for 2019, where we're now at almost 110 launches per year. And of course, there's many other future considerations for launches, where SpaceX is claiming that they're going to, on their own, conduct 50 launches in a year, making a substantial contribution to growth that might surpass this fairly modest 6% per year. And so the other aspect associated with this modern space sector is that there are also launches taking place in far more locations in the world, in particular pivot towards more launches closer to the tropics. So this has potential for implications for the impact on the environment, because we now have more pollutants being emitted into more locations on the Earth. Even the UK has joined the race and is certainly not holding back. They've gone from having no spaceports to promising to develop 7 spaceports. They were supposed to be operational last year. They've been delayed a bit. The plan is that many of these will be operational by this year. 5 of these are located in Scotland, in quite remote locations as well, like Shetland Islands. There's also one in Wales, in Snowdonia, a coveted national park, and then one in England located in Cornwall. And so for the UK, it's going to be a mix of vertical launches, the sort of traditional rocket launches that we're more familiar with, but also horizontal launches, where essentially the launch takes place along a runway similar to an airport. We're also seeing that increasingly space is littered with more and more discarded rocket parts, spent satellites, and other junk that is building up within space. One to note is that the second stage discarded component of one of the SpaceX launches from 2015 is hurtling towards the moon and will add a new crater to the far side of the moon. NASA predicts that this is going to happen by the 4th of March. And in addition to this, we have these components that are also re-entering the Earth at certain points and burning up through the mesosphere, the layer of the atmosphere about 50 kilometers overhead. In addition to that, there's also astronomers who are particularly concerned about this buildup of junk and satellites, functional satellites within space, because it does obscure their vision into outer space. And so there's not just environmental sciences communities and policy development communities concerned about this, but also astronomers and many other communities. Just to bring to bear how important this buildup of space junk is, we can see this time series of the number of re-entries of space debris and also reusable components that has changed substantially since the first space race, where we saw a peak of about 500 odd components re-entering the atmosphere, to a lull of somewhere around 20 to less than 100 re-entering components. And very recently, we're starting to see this dramatic spike from less than 50 in 2016 to almost 400 documented re-entering components in 2020. And some of this is from very recent rocket launches, but some of this is also quite historical components that they can date back to the 70s and to the mid 60s. And so there's reasons why I'm presenting this. There's concerns over the air pollution that can be generated when these reusable components burn through the atmosphere, but I'll go through those details a little bit later in my presentation. I've mentioned this reusable components aspect quite a few times. This is incredibly important because now more and more components are reusable. We've seen this demonstrated by SpaceX, where they showed that you can have a reusable booster, the first stage component of the rocket launch. And so you can revive it, regenerate it, and use it again. So it contributes to a decline in the number of material items that are needed to build rockets. But as I'll show in a few slides, it can contribute to an increase in air pollution. And of course, we have reusable components for space travel. So moving amateur and professional astronauts into orbit or to the International Space Station. And of course, I'm showing the modern space sector and a historical space shuttle, which last launched in 2011. But it's just to show that there's also space pods, space shuttles, space planes that need to return and burn their heat shields through the atmosphere. So with this in mind, the pollution that's being produced that can contribute to a change in the chemical composition of the atmosphere and also contribute to changes in climate is coming not just from the combustion of rocket propellants during the launch phase, but also from these re-entering components that have heat shields that burn on re-entry and also burn up of space junk, and hopefully 100% burn up. Otherwise you have parts trickling down to the surface of the Earth and causing hazards as they do. I should mention just some jargon. So a propellant is the combined fuel and oxidizer. And I'll go into specific details about the kinds of fuels and oxidizers that are used by the space tourism industry in a few slides. Space tourism is not new. It did happen very infrequently, maybe every year or every second year between 2001 and 2009, where very rich people could afford a ticket to go to the International Space Station on the Soyuz rocket, which is a Russian-owned rocket, for an inexpensive ticket of just over $20 million US. And of course, I remember this from being based in South Africa during my undergrad, when it was noteworthy that a South African managed to afford a ticket. So Mark Shuttleworth, whose company is known for developing Ubuntu, the open source Linux software, and he conducted this flight in 2002, which makes him one of the first to do this. But of course, this form of space tourism, going to the International Space Station, largely ended in 2009, but has actually revived itself with a recent launch in December 2021, where a Japanese fashion tycoon bought a ticket to go to the International Space Station. But now, of course, we're entering this new era of billionaire space tourism, where we have these three very rich people who can afford to develop and pay for flights to go up into space or close to space, or go into orbit around the Earth. And so we have Elon Musk with his SpaceX company, we have Jeff Bezos with Blue Origin, and then we have Richard Branson with Virgin Galactic. And I'll take you through all of the processes that took place in the individual missions that were carried out in 2021 to put perspective into the kinds of air pollutants that can be produced from their missions that have been carried out, or their space tourism offerings. So to get us started, we had our first space tourism billionaire launch by Virgin Galactic, which took place on the 12th of July, 2021. So he officially won the race, but of course he's been contested by Blue Origin because he only reached an altitude of 86 kilometers. And so he didn't cross the Kármán line, the international line that's known as, or internationally recognized as, truly reaching outer space. So for his space tourism offering, it's somewhat different from the others in that he has a horizontal launch. So the mechanism behind it is that a rocket is carried on this White Knight carrier aircraft to about 15 kilometers altitude, and then the rocket launch occurs at this altitude. So that's just at the cusp of the stratosphere. And then the rocket launches, and effectively the rocket is the space plane, VSS Unity space plane. And of course, the launch process is an hour or 2 hours or more, and you can watch the whole thing evolve on YouTube. But the actual process from the aircraft actually taking off is about just shy of about 20 minutes or so. It's a very short-term experience, just reaching the edge of outer space. Then Blue Origin did their space tourism offering or demonstration just a few days after Virgin Galactic on the 21st of July. And so, of course, Blue Origin was outcompeted by Virgin Galactic. But if you followed the space tourism missions that have carried out, they're somewhat PR focused. And so what they strategically did is they chose for their demonstration mission to occur on the anniversary of the moon landing, so the 21st of July, where it occurred in 1969. They made sure that they reached an altitude of 105 kilometers, passing the Kármán line, offering tourists the opportunity to truly go into outer space. They've also carried out more launches since, so they've had 2 more launches, and buried within this again is a lot of PR taking place. So the first launch involved Wally Funk, an astronaut who was denied the opportunity to go into space when she conducted the training alongside other male astronauts. So definitely an important person to finally get the opportunity to experience going into outer space. William Shatner has been into outer space in Star Trek, and this is the first time that he got to do it for real. And I think at the time he was the oldest person to go into outer space, but I would be probably misremembering all the other people who have been to outer space if I said he's still the oldest. And then on the third launch, they had an ABC Good Morning America host. It's not entirely clear why, because they definitely don't need additional publicity for their space tourism missions. So the launch vehicle that they use is called New Shepard. It's a launch vehicle and pod. And so you can see the pod after the launch has taken place and they've drifted back down to Earth. It's a 1-stage rocket and it is reusable. So it also has to burn through the mesosphere when it returns to Earth. And again, I've just included the link to the YouTube video if you wanted to watch the whole thing evolve if you haven't already. And then SpaceX, a few months later, so the 16th September 2021, conducted their space tourism offering. And this particular mission was called Inspiration 4. And so it included 4 amateur astronauts who were able to go into orbit and spend, I think it was about 3 or 4 days orbiting the Earth. So of course, their offering was truly going into outer space and at an altitude higher than the International Space Station. They include their reusable first stage rocket. So it's a 2-stage rocket. The first stage is reusable. The second stage is synonymous with what's hurtling towards the moon currently from a 2015 launch by SpaceX. And then they have the space capsule, which allows people to look out in the window on top as they're orbiting the Earth. The first stage, as I mentioned, is reusable, so it has to burn through the atmosphere. The discarded second stage, as long as they don't lose track of it, will eventually also return to Earth and burn through the mesosphere, and hopefully, again, 100% burn. I think I've mentioned everything on the slide again. The YouTube video is included if you want to see the launch process, and I think there's a separate YouTube video of the return process. And so, of course, if we want to talk about the potential influence of these rocket launches on the environment, we do have to understand the different kinds of propellants that are used, the composition of those propellants, and what they could potentially form under combustion in the combustion process. And so for Virgin Galactic, they have somewhat of an unusual fuel in that it's never been used for space for rocket launches in the past. Theirs is a hybrid fuel, so it's hybrid because there's two phases. There's a solid fuel, HTPB, and I'll give the acronym in the next slide when I just give a little more detail about it. But essentially, it's a synthetic rubber fuel. And of course, this isn't an ideal comparison, but it's like burning rubber tires, where you can imagine it's a far more inefficient combustion process, but you can imagine there's a lot of air pollution that's produced from rubber tires burning. So the potential to produce a large quantity of a mix of pollutants. And then they have a liquid oxidizer. For Blue Origin, they have a cryogenic fuel, and this is liquid hydrogen fuel, and then liquid oxygen oxidizer. And then SpaceX uses the fuel that they traditionally use for their Falcon 9 rockets. So kerosene, where if I think of kerosene, I'm thinking of homes that don't have access to electricity and use kerosene lamps for lighting. And then they also have a liquid oxygen oxidizer. The results that I'm going to share here aren't going to focus on the greenhouse gas carbon dioxide, but I think it's worth mentioning because there has been a lot of confusion about whether or not these kinds of fuels produce CO2. So the fuels used by Virgin Galactic and SpaceX are carbon-based fuels, which means that when they undergo combustion, they will form CO2 or carbon dioxide. Whereas the cryogenic fuel from Blue Origin doesn't include any carbon. So when it burns, it's not going to produce any CO2. But it is worth noting when I get to the next slide that it is producing water vapor, and water vapor is a greenhouse gas. So it's certainly not devoid of producing greenhouse gases, it's just not producing CO2. And so this just gives a little bit more illustration of this HTPB fuel, which is somewhat unique to Virgin Galactic. It's hydroxyl terminated polybutadiene, essentially a carbon-based fuel that produces CO2 under combustion. I can admit freely that I am not a rocket scientist, but I did find it interesting to see how this fuel is included in their rocket. And so what it is essentially is in the middle is a combustion chamber. Around this is the fuel, the synthetic rubber, and then there's also a casing. So the combustion chamber is where the oxidizer passes through and the combustion process takes place. It generates a lot of energy, which allows for the launch process to take place. And of course, I've included a link to the peer-reviewed paper where I found these images if you want to find out more. And so now we move on to understanding the kinds of dominant air pollutants that can be produced just from the launch process from these three kinds of rockets. So Virgin Galactic and both SpaceX are carbon-based fuels. So they're going to produce similar kinds of pollutants, but in different quantities. So both of them will produce water vapor because they include hydrogen and in the fuel, and also an oxygen oxidizer. And then also importantly, they're both going to produce black carbon particles or soot particles. So I don't know if you've ever seen a large heavy duty vehicle first sort of turn on their ignition. Typically you'll see coming out of the exhaust quite a large plume of black smoke, and that black smoke includes a lot of these soot particles, just for relatable context. I've mentioned that Blue Origin will produce water vapor because of the hydrogen-based fuel. And something else that's ubiquitous amongst these rockets is nitrogen oxides, or NOx. And the dominant source of NOx is not actually coming from the fuel, but it's coming from the very high temperature process during the launch. And because this process is very high temperature, it provides enough energy to convert unreactive nitrogen in the atmosphere into this reactive nitrogen or nitrogen oxides or NOx. We have about 79% of the atmosphere's composition is this unreactive nitrogen, so it's abundant. There's a lot around to convert to these nitrogen oxides. So if I do mention this as thermal NOx, I'm referring to this high temperature process that yields these nitrogen oxide pollutants, whereas the others are predominantly, if not exclusively, coming from combustion of the fuel. So that's the launch phase, but then also there are these re-entering reusable components. And so I've mentioned that Blue Origin is a single stage rocket and it is reusable. So it does have to come back down to Earth. It has to traverse the mesosphere. And during this process, it has heat shields or whatever else is being used to protect it that burn through the mesosphere on return. SpaceX, the same thing, the first stage or the booster stage of the rocket has to return. And then of course, there are these pods or capsules that return, and they return at a high velocity through the mesosphere, and so do produce nitrogen oxides. The Virgin Galactic flight, at least as best as I understand it, has this feathering system that essentially slows it down enough so that it doesn't undergo ablation or burn through the mesosphere. So it's not going to contribute substantially to this nitrogen oxides emissions on return. At least as best we understand it, the amount of NOx that's produced from this re-entry process is proportional to the mass of the rockets that are returning. And so we can use this to constrain the emissions that will come from these rockets when they return, and also the pods and capsules carrying the amateur astronauts. And then, of course, given this information, we can now look at this very evocative tweet by Blue Origin that was posted possibly soon after Virgin Galactic launched or announced their launch. I forget the exact date, but it's not hard to find this online. And so Blue Origin compares their offering to Virgin Galactic, showing that they're better in all ways. So they fly above the Kármán line. They have, I guess this is better, a rocket rather than an airplane. So I guess you don't get a unique experience. They have larger windows. You just get airplane-sized windows, which for us, I suppose, during COVID is maybe a novelty now because hardly anyone can fly. An escape system. I don't know any details about this, but I assume it's good to have an escape system. And then the environmental impact, and one component of the environmental impact. And so they mention this ozone layer impact. So what they're referring to is ozone in the stratosphere, so about 10, 15 to 30 kilometers overhead, where the ozone is concentrated. And this is really where we want ozone to be. Ozone in that layer protects us from harmful UV radiation. And so if there is an impact, if it contributes to the depletion of ozone, it allows for more of these harmful UV rays to reach the surface of the Earth and cause things like skin cancer and have other impacts on the environment. So Blue Origin's claim is that it's minimal. All they produce is water. And the Virgin Galactic, they claim, is high because of the combination of fuel types that are being used. And they quote a recent study which looked at somewhat synonymous rockets between the two. Rockets that are launched by the two companies. And then, of course, the flight history. Look, we have a greater heritage of 15 safe flights. You've only done 3 and you only go up to 80 kilometers. We're going to unpack that ozone layer impact a little bit more with the kinds of research that we've carried out in our own group. And of course, with the context of the previous slides, we know that water is not the only thing that's being produced by Blue Origin's flights. The NOx is being produced during the launch, and of course is being produced when they return on re-entry. And so the air pollution that we're particularly concerned about from these rockets are things like black carbon or soot. And the reason that we're very concerned about this is because soot is a very efficient absorber of incoming sunlight. And the closer the soot is to this incoming sunlight, so higher up in the atmosphere, the more efficient it is. The IPCC has determined from an exhaustive list of current knowledge that black carbon or soot particles are the third largest climate warmer, or have the third highest radiative forcing after carbon dioxide and methane. So it's a particularly concerning climate forcer. It's not categorized as a greenhouse gas, but it certainly is a relevant climate forcer. And then we have water vapor, the supposed innocuous stuff that's produced by Blue Origin, and also nitrogen oxides produced by all launches and during re-entry that have the potential to deplete ozone in the stratosphere by promoting this conversion of ozone to oxygen. Oxygen is clearly not something that we're particularly concerned about, but it's this depletion process, taking more ozone out of that layer that is really important for protecting us from harmful UV radiation, and also a layer in the atmosphere that has, through the Montreal Protocol, started to repair itself after the banning of ozone depleting substances that are produced from earthbound sources. The other concern with rockets is that they're not just bound to the Earth. The industries on Earth and the aircraft produce emissions that have to work quite a bit harder than rockets to reach the stratospheric layer to go on to have an impact on ozone, whereas rockets are just injecting these right into all of the layers in the atmosphere. And so just for context, I've indicated the general layers that the rocket reaches. I've maybe cheated a little bit because I haven't actually shown the altitude at which the engines cut off, which is always a little bit lower than the altitude that the rocket reaches. But just for context, the Virgin Galactic flight goes to 85 kilometers within the mesosphere. Blue Origin goes up to 110 kilometers, reaching the thermosphere, and then SpaceX 505 kilometers, also reaching the middle to upper thermosphere. And then we have these re-entry ablation emissions, which occur throughout the mesosphere, extending also into the upper stratosphere. And so what we did for our research to try and understand the potential impact of the space tourism industry on the environment is we developed an inventory of the air pollutant emissions from a speculative space tourism industry. So let's imagine, hopefully far into the future, we have this formidable space tourism industry that has routine launches from all of these three players. There are, of course, other players that are considering, or at least starting to develop a space tourism industry. China is starting to build a space plane. India has had rumblings of putting together a space tourism industry as well. So it's certainly not exclusive to these three companies. And so what we do is we assume that there'll be daily launches from Virgin Galactic. And this is actually quite modest in comparison to what they've announced. They say that they're going to do 400 launches a year. Blue Origin, we say daily launches, and perhaps we're being a little bit generous with the frequency with which they can actually launch their rocket, because there is a time delay between their rocket arriving back after a mission and having to be restored and regenerated for reuse. But that restoration and regeneration, they're starting to reduce the amount of time between it. Who knows, they could build more rockets so that they could sustain something like daily launches. And then because SpaceX goes into orbit and spends 3 to 4 days in orbit, we assume that it would probably be something like weekly launches. And so what we do is we calculate the emissions of all these different air pollutants and also consider the re-entry burn that would take place from all of the reusable components. And just to compare the values that we obtained specifically for this re-entry process, we evaluated against the natural NOx that comes from meteorites. So meteorites burning up as they burn through the mesosphere. The estimate here has a very wide range because there is some uncertainty in documenting the amount of mass of meteorites that burns through the mesosphere, but the range is about 2 to 40 kilotons. And we can compare this to our space tourism industry scenario and just routine space junk that re-enters from past launches and satellites is about 5.5 kilotons of NOx. So we're starting to see that with a formidable space tourism industry and ongoing standard rocket launches, we might start to compete with the natural NOx that comes from meteorites. So again, our anthropogenic influence is starting to offset the balance of natural NOx in this layer in the atmosphere. We then take our emission inventory and run it through a 3D atmospheric chemistry transport model, which is able to reproduce all the complex chemistry that takes place throughout the atmospheric layers. It also accounts for transport of these air pollutants and also loss processes of these air pollutants. The chemical transport model that we use is the GeosChem model. It's a publicly available model. You can find out more from the website. It's used, developed, and maintained by the user community, and it includes an exhaustive list of earthbound emissions already. So there's sort of the standard baseline atmosphere represented in the model, and on top of that, we add our space tourism and standard rocket launch emissions to the model. There's also meteorology that's accounted for from a NASA meteorological product that they develop and maintain. And then importantly, this model is coupled to a radiative transform model, which allows us to determine the imbalance between the amount of light, energy, or radiation that's entering the atmosphere versus what's leaving the atmosphere. And this allows us to assess the contribution of these air pollutant emissions to offsetting this radiative balance. And so what we do with this model is we essentially run it without our rocket emissions and with our rocket emissions. We can take the difference in the results from these simulations and determine the effect on chemical composition, the concentration of chemicals in the atmosphere, most notably stratospheric ozone, and then also on radiative forcing, the warming or cooling contribution of these individual air pollutants. And so what we have here is the results that come from that simulation. I'll just take you through the different components to these results. So the colors indicate that there's a decrease due to space tourism emissions in blue, or an increase due to space tourism emissions in red. I'm just showing 3 different chemicals here: the nitrogen oxides, water vapor, and then ozone. And the results are showing the vertical distribution of these in the atmosphere. Also indicated is the boundary between the stratosphere below and the mesosphere above, and then the boundary between the stratosphere above and the troposphere below. And then other aspects is that it's a latitudinal profile. So it takes us all the way from the southern hemisphere to the northern hemisphere, averaged across the whole longitudinal range of the Earth. So the first result is NOx. Nitrogen oxides are coming largely from these re-entry ablation emissions. And so we see a large enhancement in the mesosphere as we'd expect. Most of these launches are in the northern hemisphere, at least from the demonstration missions. So the enhancement is greater in the northern hemisphere. We see water vapor as well, similar location of the enhancement. The water vapor is also coming from the standard rockets for the second stage launch. And so we do get a slightly higher contribution of water vapor emissions higher up in the atmosphere. And then the influence of ozone. So this is where the model really does the hard work, because ozone chemistry is complex. Ozone is a secondary pollutant. We really rely on the model to represent the changes in ozone. And so what we're finding is this general depletion of ozone reaching in some locations up to 8 parts per billion. And I'll put that number in context shortly. But if we take the average decline in ozone across this whole stratospheric portion, we're finding that the decline is less than 0.1%. And again, putting that number into context, this is much less than the 1 to 2% decline in stratospheric ozone that resulted from these earthbound ozone depleting substances that were banned through the Montreal Protocol. But this 1 to 2% really does highlight how sensitive the stratospheric ozone layer is to these changes. 1 to 2% has the potential to have a really large influence on the amount of UV radiation that reaches the surface of the Earth and goes on to impact humans and the environment. So the overall conclusion from this analysis across the stratosphere is that the effect throughout the stratosphere is quite small. But if we really hone in on this enhancement that takes place in the northern hemisphere in the higher latitudes, in particular in springtime, when we start to see a maximum ozone depletion, we're finding that the ozone depletion per decade reaches about 16 parts per billion. And again, I'll put that number into context. What this is showing here, this image, is the time series of the decline in ozone in this upper stratospheric layer in the northern hemisphere high latitudes over time. Blue is the southern hemisphere, red is the northern hemisphere. The dotted line is just for routine rocket launches with a 5.6% per year increase. So following the same increase I showed in one of the earlier slides. The boxes show what happens when we include 3 years of space tourism emissions, just how much more the decline is in ozone as a result of introducing space tourism into the northern hemisphere. I should mention that 3 years is key because it does take 3 years for the chemistry in the stratosphere and mesosphere to evolve. It's more long-lived. The turnover rates of the atmosphere are longer than they are closer to the surface of the Earth. So that's why we need the atmosphere to evolve for 3 years. If we continue the trajectory of the decline from space tourism to a decade, so it's a cheaper way of doing it than running a model, which is computationally expensive, we find that the space tourism industry with routine launches, as we've represented them in the model, has the potential to reverse 20% of the recovery in stratospheric ozone in this region that's been observed and been attributed to the Montreal Protocol ban on ozone depleting substances. So to put the 20% reversal into context again, what this is saying is that it could take 10 years to undermine 35 years of progress through the Montreal Protocol. Okay, I'm being generous. It's not yet 35 years, but it's really close to 35 years. They celebrate this anniversary very soon. And so this is just incredibly worrying. It took a lot of resources, a lot of energy. It took bringing together the international community to develop the Montreal Protocol. We still laud it as a success story for addressing atmospheric pollution, especially when we look at how hard it has been to achieve similar progress with climate change. International regulation associated with greenhouse gases and the impact they have on climate change. The other aspect that I mentioned that we're quite concerned about is the radiative forcing or warming that will result from emissions of black carbon or soot from the space tourism industry, but also just this routine underlying rocket emissions that occur that put weather satellites and research satellites into orbit. And so again, with our model coupled to the radiative transfer model, we're able to calculate the radiative forcing or the milliwatts per meter squared that will result globally due to the inclusion of soot emissions from space tourism rockets, in particular Virgin Galactic and SpaceX. We can see there's some spatial heterogeneity in this. The largest amplification of warming occurs over the Arctic. The smallest warming is occurring closer to the tropics. And the warming that occurs in the Arctic can reach as high as 30 milliwatts per meter squared. Again, I'll put this into context. And we can get a global average of close to 8 milliwatts per meter squared. We also consider other aspects that could contribute to radiative forcing from rocket emissions. I'm not going to go into all the details of this on this side, but just to point out that when we do look at the contribution from individual components, we find from 3 years of space tourism emissions that the dominant component contributing to warming is soot particles. Any other effects have a very, very small reversal of this warming or very small cooling effect. And so to put this 7.9, almost 8 milliwatts per meter squared value into context, we compared it to what's been calculated for global sources, earthbound sources of black carbon. So industry, vehicles, aircraft, fires. There are many, many other sources that contribute to black carbon emissions closer to the surface of the Earth. And we calculate that this actually represents 6% of global warming that's been calculated on an annual average from earthbound soot sources. Even though it makes a negligible contribution to emissions, the contribution of black carbon emissions from rocket launches is less than 0.001%. And so what this means is that the soot emissions coming from rockets have a really, really high warming efficiency, 500 times more than surface sources. And this is because of the ability of these rockets to inject soot particles throughout multiple layers in the atmosphere. And so because it can inject these into multiple layers in the atmosphere, the ability of these black carbon particles to absorb incoming solar radiation don't have to compete with other sources for that incoming solar radiation or other factors in the atmosphere like clouds or reflecting aerosols and any other factors that could contribute. And also the implication of a 500 times more efficient warming is that the space industry rockets that produce soot particles don't have to increase in launch numbers each year that much to be able to have a large influence on warming. So there's a particular sensitivity to growth in rocket launches associated with these hydrocarbon-based fuels that produce black carbon. And so just to bring it all together and wrap up some of the main findings for our research that we've carried out is that the artificial ablation emissions that are coming from re-entry of reusable components and also from re-entry of space junk may actually start to outcompete natural emissions from meteorites, but we do need a better handle on those natural emissions that come from meteorites to really compare the two with greater accuracy. The space tourism air pollutant emissions that come from launches and ablation have the potential to undermine progress that has been achieved with the Montreal Protocol ban on ozone depleting substances that are earthbound. And then, of course, there is this large warming efficiency of soot particles from rocket launch emissions, 500 times more than earthbound sources. And so the small growth even a small growth in space industry may have large implications. Of course, our research is one speculation, one scenario. There's always room for improvement in the kinds of modeling studies that we carry out. We need better knowledge of the future launch frequencies of space tourism, also better knowledge of other players that are going to start to participate in offering space tourism. There's also other chemicals that are formed during the launch and ablation process that we don't capture. We capture the most well-known and what we understand to be the largest contributors to air pollutant emissions. And in calculating the radiative forcing influence of soot particles, we're only counting for the direct forcing, the direct effect of sunlight being absorbed by black carbon particles. There's many other knock-on effects that occur that we don't represent, like warming of the atmosphere, changing circulation patterns, and so on. Regardless of these aspects that could be improved in our work, there is no international regulation that exists targeting rocket launches in general or targeting specifically the space tourism industry. And so what's really crucial is that we act now to formulate the kind of regulation that minimizes the harmful impacts of an uncertain industry that's really geared towards the rich and the impact this might have on the environment for the many. And of course, thank you very much for your attention, and I'm happy to take any discussion points or questions that result from this talk. If you want to find out more about the policy relevant research that's carried out in my group, I've just included a link to our research group page. And then if you have any questions and you weren't able to ask them during the discussion session, you're more than welcome to contact me. Thank you very much for your time and attention.
Oh, thanks, Eloise. That was really interesting. So just a reminder that we'll be hosting our questions through the Slido tool, that is sli.do, the website, and you have to enter the code UCL space, all one word. And we've got a couple of questions up there now, so I'm going to start posing them to you, Eloise. So yeah, can these, got a question from Anonymous here, can these types of rocket launches be used in any other way for research or other benefits? Or are they purely just for entertainment?
Oh, that's a great question. That's a question that has come up a few times as well. And there certainly are, the industries like Blue Origin have certainly said things, sort of throwaway statements of how these can contribute to enhancing research and understanding of the environment. And I think the other companies have mentioned that too. I'm just remembering Blue Origin stating that. But I haven't seen any kind of substantive evidence of what they're going to do, in what way they're going to help enhance research that's already being carried out to understand space travel. One of the potential things that's been floated around is the ability to put instruments onto their specific pods and make measurements of the vertical distribution of atmospheric composition or meteorology, but I haven't seen anything develop further than the sort of mention of this.
Right, and I guess we got a question here that I think I'm gonna add on to it. But in terms of the emissions generated per flight, how do these launches compare to cargo ships or to aircraft? Yeah, how much worse is it? And how does the altitude depend to affect this?
Yeah, that's great. And I did only do a comparison between meteorites and the ablation emissions, not so much the sort of holistic number of NOx emissions or black carbon emissions. Although I did show black carbon is sort of 0.001%, and that's not unusual. The NOx emissions, the black carbon emissions, the water vapor emissions that come from these rocket launches are much less than come from, say, the aircraft industry or from shipping. Aircraft industry pre, post, and during COVID. But the issue, of course, is that they are able to be injected into multiple layers in the atmosphere. And in those layers in the atmosphere, they can persist for much longer than they persist from these surface-based sources. So it's important to realize that even if we compared sort of number of NOx molecules across these different industries, it wouldn't be a fair comparison because the influence that they have is different because of where they're emitted and how long they persist.
Yeah.
And I guess to add to that, this is why we need something like chemical transport models, maybe sort of innovative observing platforms as well, to start to see the influence of these rocket launches on the atmosphere to support the kinds of modeling results that we're obtaining.
So Jordan Stone's got a question. It sounds like you had some quite reasonable basis for the assumptions about Virgin and Blue Origin. But how about SpaceX? What are their plans for space tourism? Was inspiration for just a one-off stunt, or was it something they really plan to build on?
Yeah, that's a great question, and it's a fast-moving field, so it's sort of hard to keep up with the latest sort of press releases from these companies. SpaceX is somewhat of an unusual mission in that it was commissioned not by Elon Musk, but by someone else similarly with lots of money to do so. And so it's not clear whether SpaceX is actually entering the space tourism race or if they just wanted to do this demonstration because someone put the money forward to do it. But perhaps there's potential for them to start to join the kind of International Space Station space tourism offering. They've already sent astronauts to the International Space Station. But that's a great question. There is a lot of uncertainty about what SpaceX will actually offer in the future, if anything.
Okay, just a reminder, the website is sli.do and enter the code UCL space. We're running a little low on questions, so more would be appreciated. Oh, we've got some more coming in already. That's great. So I guess I had a question kind of related to that. You're talking about one of the ways in which rocket flights might increase in the future. It's the space tourism industry that's going from zero to something. I guess there's other uses of space that have been accelerating over the past decade and the future. And I guess if SpaceX gets its way with the Starship, they plan for the only limiting factor to be the time to refuel and the cost of the fuel. And so I guess they're intending to do many, 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 many launches with this the largest rocket ever. How big will these other developments in rocketry be compared with these space tourism projections you've made?
Yeah, there's a little bit more certainty associated with some of the sort of growth in the standards rocket launches, like SpaceX's Starlink, essentially allowing access to internet across the world using satellites. In terms of that growth, we have a very modest growth represented in our simulation, 5.6% per year, but that's based on business as usual. The kind of murmurings from all of these space industry companies is that is going to substantially ramp up, especially when we see somewhere like the UK building 7 spaceports, not even a modest one as a trial. They're going all in. So there is the potential for the standard rocket launches to also increase substantially. So for SpaceX, of course, it's a kerosene-fueled rocket. Produces a lot of soot particles. So there's definitely concern over just the standard growth in rocket launches. But I think if we're going to develop something like environmental regulation, it doesn't have to exclusively target space tourism. It can target all rocket launches to ensure they at least minimize their environmental impact.
A quick follow-on. I know the Starship is going to use a different fuel source. It's going to be methane fuel. Mm-hmm. Will that be cleaner? Is that better?
So it has the potential to be worse than the Blue Origin hydrogen-based fuel. It's carbon-based, so it does produce CO2. Depending on the burning efficiency, it could also produce soot particles. And of course, I am only focusing on the launch and re-entry process. There's this whole lead up towards that can contribute to air pollution emissions that worsen the environment on the ground as these things are built, as methane fuel is extracted or produced.
So I guess this is a clarifying question. So are rockets a significant source of CO2 emissions?
It depends. So no, on an absolute amount, compare CO2 emissions from rocket launches to CO2 emissions from the aviation industry, and the CO2 emissions from the aviation industry are considerably higher. But if you're a person who is maybe counting their CO2 footprint on the environment, if it's just 4 of you flying into outer space for a very expensive selfie, your CO2 footprint is considerably higher than if you were doing a long haul flight.
Right. So you mentioned this is an area that might need regulation, and we've got a question here asking, what are some examples of policy that could help reduce these impacts?
This really depends on what kind of limits we have technologically. We do have emission control measures that exist for earthbound sources. Are those the kind of technologies that we could adapt to reduce the emissions coming from rocket exhausts? We have vehicles that are regulated, the exhaust emissions are captured, and is that the kind of technology that we could use for rocket exhaust emissions as well? I'm not sure, what the technological limitations are.
Yeah, I guess the challenge with rockets is weight's at a premium and efficiency is a premium. So I mean, I guess the big one would be choice of fuels. I mean, I guess you talked about a bunch of these different fuels. Is there any fuel out of those that you'd recommend as the sort of least environmentally impactful?
I mean, perhaps the cryogenic fuel is the least hazardous in the combustion process because it doesn't include the soot particles in addition. But I don't think it can be used as widely for all rocket launches as it's being used for space tourism. It's not used in general for the first stage process. So it's not, I think, a highly adaptable fuel type. And of course, there are researchers working on trying to identify less hazardous fuels, but many of them are at the pilot stage or the testing stage. So it's not clear whether they can actually be realized.
So you mentioned, I guess, NOx appeared quite heavily due to the ablation that comes down. But I guess another aspect of the ablation, asked here by Chris, is what's the impact of the space junk? Because presumably, when the material burns up, you're adding, burned up versions of all the chemicals and compounds that were in the satellite. Are there any things that you might worry about that are added beyond the sort of NOx emissions that come from burning up these satellites?
Yeah, it really depends on the chemical composition of the materials that have been used to produce that satellite. If, say, it's predominantly aluminium based, that can produce aluminum oxide, Al2O3. That is of concern because it does alter the radiative balance of the atmosphere. It also contributes to, it increases the rate of ozone depletion in the stratosphere. And of course, I mean, there's so many different compounds that go into the sort of manufacture of those satellites that there's a myriad of pollutants that are coming from that re-entry burn process that we're not representing with our model, but perhaps we also need a better handle on how we could represent those and what happens to them once they're emitted into the atmosphere. But yeah, great question. Yeah,
so I guess I've got one here, kind of related to an earlier question. Is there anything we can do to make launching rockets more sustainable? Any developments?
Yeah, I suppose it's related to the previous question, which was on, are there any regulations that can be imposed? I think there would have to be technological advancements that could help prevent pollutants produced during the combustion process from being released into the atmosphere. There is, of course, we don't want to send all of our second stage rockets hurtling to the moon, but someone who did write a piece in The Conversation talking about how there's almost a trade-off. At least that second stage rocket that's hurtling towards the moon isn't going to contribute to buildup of pollution in the mesosphere. Not an ideal option though. And there are, I think the European Space Agency, many other companies now are thinking of ways to clean up space junk that doesn't require that it gets sent through the mesosphere and burned up.
Right.
Yeah.
So I guess someone's brought up the question, you talked about how satellites or these re-entry and the emissions are now rivaling the natural sources of NOx in the mesosphere. But how do we determine how much meteoroids are adding? How can we narrow that huge uncertainty bound?
Yeah, so there's a really great review paper by John Plain from University of Leeds who talks about the information that we have about the amount of cosmic dust that reaches the surface of the Earth, or that's been documented to pass through the mesosphere, that provides us with some constraints on the mass of meteorites that pass through the mesosphere each year. So of course, this is a review paper that collects information from multiple papers, and that's why we get this range. But there are also researchers looking at whether we can identify meteorites passing through the mesosphere using satellite observations that document anomalies in light. So these satellite observations are typically used to identify flashes from lightning, but with smart machine learning techniques and other approaches, we can actually start to characterize whether it's lightning, whether it's meteorites, and hopefully also artificial components. So I've had discussions with the person from NASA who's putting together this data set to see whether we can start to get a better handle on both those components, meteorites and artificial components.
So I guess, yeah, the ozone results were the ones that sort of worried me the most out of the things you were saying. And someone's asked this question: which of the companies, which of these plans that you assessed contributed the most to the ozone destruction that you observed in the models?
Yeah, it's probably not going to be a very comforting result, because it is coming from the re-entry process. So we're seeing that the largest contributor is nitrogen oxides, and nitrogen oxide emissions are largely coming from that re-entry through the mesosphere. So, that's maybe the aspect that we might want to target if we wanted to reduce the ozone destruction that could result from a large-scale space tourism industry.
And so I guess with the regular ozone hole, this is due to the buildup of long-lived CFC gases. So it's a problem that accumulates. Even once you've stopped emitting stuff, the problem is going to be persisting for a very long time.
Yep.
Is that the case with this kind of an ozone loss? Is it an accumulating type, or is it something that will, if we stop the emissions tomorrow, the ozone effect will stop as well?
Yeah, I think from the modeling studies that we're doing, the legacy wouldn't be as long. So those ozone depleting substances are catalysts in the stratosphere, so they regenerate themselves and they can last there for a very, very long time. Whereas the nitrogen oxides and the water vapor and all the other components that we're representing that could deplete ozone don't last in the mesosphere and stratosphere as long as these ozone depleting substances. They also aren't as reactive in depleting ozone as the ozone depleting substances, but because we are continually putting NOx emissions into that layer of the stratosphere, we're continuing to chew up ozone in that layer.
So another question related to efficiency, I think, or reducing this impact. What can space companies do to reduce their emissions? If you're trying to, would buses be better than these sort of small 4-person launches? Get 100 tourists up at once? Would that be more efficient?
I think we're maybe going to find that out. So China is building a space plane that will host more people than Virgin Galactic. So that's the comparison, the space plane for Virgin Galactic. But I did just check on this yesterday, and now I've forgotten exactly what number of people. It was something like 16 or so. So yes, okay, you can take more people to space, and so the per person emissions would decline, but it really just depends on the frequency with which we launch these rockets into space.
Right. And I guess there's a question here. How sensitive do you think the billionaires are to the concerns you've raised?
I can't really claim to have had a personal discussion with them to find out. Oddly enough, I'm not within their social circles. Yeah, I don't know that I could answer that. You know, they're at least Blue Origin has shown that they're very PR focused. Their tweet has indicated that they have this sense that their rockets are having very small impact on the environment. I don't know if they're picking up and reading the literature that I'm writing, or the media interviews that I've had, to find this out. So it's a hard one to ask, but it would be interesting to see how they would respond.
Well, then I guess the question is, how seriously do you think policymakers are taking this question, or are they just keen on promoting this new industry?
I've definitely seen the media respond in a strong way to the environmental component associated with space tourism. I've been very impressed with how the media has actually made an effort to report on the potential environmental impacts. In terms of environmental legislation, we didn't see it show up at COP26. So, you know, it doesn't seem to be in the rooms where the big discussions are happening around international regulation. So perhaps not as mobilized as I think they should be.
All right. Well, thank you very much, Eloise. This was really fantastic.
Thanks, Pete.
Yeah, so thanks, Eloise, for a presentation. Thanks, everyone, for joining, for interesting questions. And a reminder, there will be another lunch hour lecture on Tuesday, 8th of February, where Dr. Julia Shaw will ask, can false memory memory evidence sway a trial? Interesting. Thank you.